Good, good. Okay, perfect. So let's see what we have today. Actually, very important topic today. We finished instruction set architecture, instruction set for RISC-V and format, of course. That was so important actually to design a computer. First part is instruction set architecture. Today we're going to start about ILU. You had lots of stuff in digital logic about ILU. You know how to multiply. Yeah, I know. But you didn't design the hardware, but you know how to add, subtract, like second complement, those stuff, you know. Very good. If you don't know, that's your problem. You need to go and review, okay? So, but I'm not going to ask about those stuff. What we're going to talk today is how to design ILU, arithmetic and logic unit. We consider that as a one block box. So it gets some input for our architecture, 64-bit, 2 input, 64. They can come from registers, or they can come from immediate part of the instruction, immediate values, and they can create 64-bit output. Some other output, like 0, for example. We also have actually some other input that we call them control input. This control input specifies which operation this ILU doing. Okay, good. So that's how, like a black box of the ILU. But what ILU doing? All of instruction that we learn, arithmetic operations, add, subtract, add, immediate. And we're going to see today some other instructions like multiplication and division. I'm not going to talk about division, but multiplication is very similar to division. You can learn that by yourself, I mean division. And we're going to see about logical operations and or XOR and shift operations. Okay, they're all part of ILU, but what about the last one? Comparison and branch is also considered some part related to ILU. Why? Because in comparison or branch, we need to compare two things, and comparing can be done using these like XOR, for example. So that's why this part also need ILU operations. Okay, I talk slow, means it's important. Okay. Also, what other things ILU need to do? ILU need to do some immediate extension, like sign extension or 0 extension. This is also part of ILU job. You know, when you do add immediate is sign extended, and like we also can do 0 extent. So you write that and this 0. Anyway, I'm not sure if I wrote these examples correctly, but we need some instruction do sign extension and some 0 extension. That's part of the ILU as well. Okay, when we're dealing with ILU, we always need to worry about one thing: overflow. So in RISC-V, the structure that exists, there is no mechanism to find overflow. So the father of this processor, that was MIPS, actually, MIPS had some mechanism inside ILU to detect overflow, but this doesn't have. So who need to worry about? Who need to fix it? Who need to actually check it out, in your opinion? Because there is no hardware mechanism inside ILU to check overflow. So who need to be worried about it? Who need to fix it? Who need to check it out? Who? Programmer or compiler. So the compiler or programmer need to worry about that. That's why we just give it to compiler to fix it. You don't need to have a hardware to detect overflow. because this is sometimes messy and complicated because we have different type of overflow. Normally, overflow happen when you have a fixed register like 64, and this is like sign. You are putting a sign value inside, like sign integer, for example. And in computers, I can say maybe in all of computers, actually, we consider negative numbers with 2's complement. When we consider 2's complement, the most significant bit always is sign. Most significant bit is always sign. So it means the range of numbers is between, if you have, for example, 4-bit, the range of this 4-bit is from 2 power 3 minus 1 to 2 power minus 2 power 3. So it means between 8 to minus 8 to 7. Why? Because for this case, minus 8 is 1, 1, 1, 1, and 7 is 1, 1, 1, 0. Why this is minus 8? Because it's 2's complement. This is 2's complement. How we can find it? To, in 2's complement, for example, this is 8. This is plus 8. To find minus 8, you just need to find the complement of this, that this is complement, and plus 1. Added 1 is going to be, right? Oh, yeah, 1, 1, 1, 1. Like 11, again, 1, 1, 1. So this is going to be minus 8. So this is how we find negative numbers. We do 2's complement. The 2's complement is like that. We negate it or we convert it. We complement it and plus 1. Okay, that's why the range is between this. So in general, if you have n binary number, the maximum positive number is 2 power n minus 1 minus 1. And the negative one, the minimum number is a negative minus 2 power n minus 1. And that's example for 4-bit when n is 4. Any question about this? You had that. That's why I go fast, because you had this stuff in digital logic. Okay. And but so in this case, you have a limited size for binary numbers. First of all, binary numbers or any numbers is just representation of some bits. It's like convention. You are just considering, okay, we are considering binary, so we are dealing this type of format for digital numbers. Okay. So let's see when overflow happening. Overflow happening in 2 cases. First, if the result exceed the range of the place that we consider. So when we add something, we have 1 carry, for example. When multiply, because, for example, in multiplication, this is happening a lot. Because if you multiply 2 binary that they are n, the result is 2n. So you can't fit it in 1 register, for example. If you multiply 2 registers, you need adding 2 registers as output. Okay, anyway, so this is one. Another case is when the sign changing. You're doing one operation, you even don't get more. You don't exceed from that representable range, but the sign changing. The sign changing, and that sign changing the sign is actually making problem. So for example, imagine we are adding 2 registers, like A and B. Overflow happening if, for example, these 2 numbers are positive, but the result become negative, or they are negative, but result become positive. And in actually subtraction, this is happening too. For example, A is bigger than B, so A is bigger than B, but the result becomes, because when A bigger than B, the result not supposed to be positive, but becomes negative. And sometimes A smaller than B, the result supposed to be negative, become positive. So this is simple. So you can understand this is overflow. But in general, in RISC-V, we don't have any mechanism to detect this stuff. So all of them need to covered by programmer or compiler. Okay. We want to see how a microstructure of the computer can get designed. From now, we are going to designing a different part of the computer in a microarchitecture part. So we talked about software part. We said, okay, the software abstraction and then instruction set architecture abstraction, that we finished it. And right now we are one layer lower. We are in a microarchitecture layer. In microarchitecture layer, we want to see how we use these blocks that we learn in digital logic to connect them together to make like a bigger architecture. Like, for example, let's do adder. Add is, most of the OLU is adding, even multiplication is a kind of addition, and shift and add also. Anyway, let's see how full adder works. We had that in digital logic. So this is the structure of full adder. So imagine you have A and B and C as a bit. This is full adder. Okay, as you can see, we have A as a bit, B as a bit, and C as a carry input carry, okay? We can consider that as a box, and we use that for making, for example, 4-bit adder, for example. But I'm gonna ask you how many layer this circuit has. How many layer? When I'm talking about layer, it means how much delay we're gonna have when we like add 2 bits here to get the result. Like, we also call that throughput. Throughput is a time that need to, when input is ready, output get ready. So this delay time is also called propagation time. Is a time that signal passing from these gates. And the layers are important. How many layers we have here? Layers is, you can consider the longest path that a signal going. So the longest path is like here. So it means 1, 2, 3. We have 3 layers, okay? So it means if, for example, propagation time for XOR is whatever, like K, for example, so we have K, K. So if they are equal, we have 3K propagation time. But this propagation time, why is important for us? Why this propagation time is important for us? Yes? It determines how fast that's going to perform. Yeah, it shows how one instruction, like add, how long takes to do that. So why again, how, but in computer, you learn in digital logic that some computers, some circuits are combinational circuits, and some circuits are sequential circuits. In sequential circuits, what we have extra, anything, do you remember in sequential circuit, what else we have in addition to this and go or and whatever? You have something else as an input. Clock. You have clock. So this propagation time specifies the clock. This propagation time, or the maximum propagation time, also called critical path. And this critical path specifies the clock, this period, clock cycle. Don't know why it's not writing good. Okay. Anyway, you can see that. Between these two rising edge, this time is the time, the longest path. So the longest path or critical path is very, very important in computer. Showing what is your clock. Because your clock need to be always bigger than critical path. If the critical path is, for example, 3K, I don't know what is K, whatever, nanosecond, whatever, or very less than that, maybe. The time that signal passing from one gate, if it's K, and if these layers become more and more, it means this clock gonna be wider and wider and wider, and the computer gonna be slower and slower and slower. If you design this properly, you might increase the speed. Why we are here? We want to learn how to design these microarchitectures or microarchitectures to run that faster. So we're going to see some tricks today to do that. One of the tricks can be done in this adder. So this adder actually called ripple carry adder. If you use 4, for example, full adder to make 4-bit adder, because carry from this need to go here and from here all down. And when this carry, for example, is not ready, these two signals cannot make the proper output. Yes, so here is so important to everything be synchronized. So this is a problem. Why? Because if we make this kind of ILU, if we make a, for example, adder like this that using ripple carry, so we need n stage for this propagation time. You know, if you have n bit, and if the propagation time for one of them is, for example, k, again, this is 3k, but imagine we just consider all of that k. If we use n bit, we need nk. Why? Because this carry need to create it here in another clock, not clock, k, go to here, another propagation, go there. And after nk, the last carry gonna get ready. And that's so slow. We don't want to waste our time. But as I said, this propagation time very important for size of the clock cycle. Okay, what we can do, in digital logic, we learned there is some way to fix that. Okay, so first of all, this is called critical path. I explained already. So the critical path is the worst case delay that happened in a circuit. Worst case delay is the worst, like a longest path that signal passing. So in this case, for 4-bit, why is worst case? Because even though, for example, you have 4-bit adder, maybe you just use 2-bit of that. That's why we consider worst case scenario. Okay, so that's called critical path. Critical path, as I said, is very important because with using critical path, you specify clock cycle. Clock cycle is the time between two rising edge of clock. This period is important to do stuff. When the next clock coming, everything need to be ready. We're going to see that when we want to design simple multiplier, we can see how this clock going to be important in that case. Okay, so this is clock cycle, and clock cycle coming from critical path or critical delay, path delay. Okay, so what is the solution? Okay, imagine in RISC-V, the model that we are using, RV64, that registers are 64 bits. We one adding to 64 needs 64K. That K is, for example, propagation time. It's a lot, lots of delay. This limits maximum clock frequency, as I mentioned. What is the solution? For solving that, there is one solution, and using a carry look ahead adder. Instead of using this type of adder, like ripple carry adder, we have another circuit here to generate. Let's have one example. I don't remember I talked about that last in digital logic, so I'm just going to have one small example. I'm sure I talk about look ahead adder, but I didn't design it. Imagine you have a 2-bit full adder. Okay, so you have full adder here, B0 coming here, A0, B1, and A1. Okay, so what we need to know, when we do adding, as you can see in this full adder, carry out is equal to AB plus C in A XOR B. Okay, as you can see in that diagram, C out, this carry out is AB, this AB, or C with A XOR B. So this is K. Okay. Can we design? Okay, as you can see, C out is related to C in. But if we know, for example, we are designing 2-bit actually adder, what about I just compute this carry in advance? Like say, okay, C1 in this case is equal to, let's consider this as a G0. G is coming from generate. And this this part, we call that P, coming from propagate. Okay, so C1 is equal to G0 plus P0 C0, and C2 is equal to, there is no space, I see, I can write here. It can be G1 plus P1 C1, but instead of using this C1, we can copy this here. Instead of using here, I use C0 that is, as this already given. C0 is always there. So we're going to add some extra circuit, but increase the speed. So this is going to be G1 plus P1. Instead of C1, I'm going to substitute G0 plus P0 C0. As you can see, C1 eliminated. We don't have C1 anymore. We just have C0, and C0 is given from beginning. This is for 2-bit. So what we are doing, we need to add a part to this. So this is the design. This is the design that I'm talking is this. Using some block diagrams that design the circuit faster, digital circuit faster, okay? So we can have G0 and P0 here. G and P, as I mentioned, generate and propagate G1 and P1. And this part called, for here is 2-bit carry look ahead. Why is carry look ahead? Because it's making carry in advance, okay? And so this creates C3. Let I change the color to make that more clear. So this is going to give you carry 1, sorry, and carry 0 is coming from output, carry 0. Okay, the output is S1 and S0. That's it. So this circuit becomes like that. Sorry, a little is small, but you can understand what's going on. We have an extra, actually, 2-bit carry look ahead circuit that this part making these two. It gets C0 and create C1, C2, whatever we want. Here we just want C1. Create that and make that ready, always ready, because C0 is always ready at the beginning. So we have all at the same time. Not at the same time. The delay that we have is probably, if the delay of this is 3K, for example, if each level is K, delay of this is going to be 4K. That is good. We are adding just one layer extra. Okay, so this is how we can make or design faster. Right now we know these layers are important. And we need to make this propagation time as low as possible. Maybe for adder, this is not visible, but imagine you're multiplying 64-bit with 64, and you need to add 64 times, and that's going to be complex. Okay, so let's see how we can. Any question about this look ahead? A carry look ahead? Okay, so let's go for multiplication. Multiplication, we had multiplication in digital logic, but we're going to explain here again. In multiplication, we have two parts, multiplicand and multiplier. And what we are doing, multiplication can happening by shifting and adding. Very simple. Imagine you have two numbers, 1, 0, 1, 0. I consider 4-bit, but it can be 16. And 0, 1, 1, 0. So how we are multiplying? We multiply 1 bit by 1 bit. If it's 0, it's all 0. And then we shift it one time and multiply again. 1 multiply to anything going to be itself. That's that one. It's going to be 0, 1, 0, 1. Again, another one. We shift. So 0, 1, 0, 1. 0, 0 multiply to anything is 0. And shift again, 0, 0, 0, 0, and then add together. So that overall going to be 0, 0, 1, 1, 1, 1, 0. Yeah, as you can see, and the rest is also 0. So that's the overall value. As you can see, if you multiply 2n bit, the result's going to be 2n bit. So for adding to 64-bit, we need 128 bits as a result. Okay, that's called multiplication, but how we can design a hardware to do that, how we can make that a macro architecture to do that. Okay, so this is the basic idea as I explained, multiplication, n bit. We have multiplicand, this part called multiplicand. Multiplicand, and this is multiplier, we call like that, multiplier and multicand. Okay, and if it's 1, we add shifted multiplicand, and if it's 0, we add nothing. So that was why how you can see in this algorithm. It's like an algorithm that you want to implement. Okay, let's see this algorithm here in this diagram. So this is the flowchart, and this is the hardware. This is important. We're going to see here how clock involved. This is very important because it's a start of seeing how you can combine two types of circuit, combinational and sequential, and how clock coming in this between. Because when you have a control making those control signals and waiting for clock coming, operation finishing. Okay, but this is algorithm. Algorithm is very easy. You are starting with testing, multiplier, least significant bit. So I write this again to don't forget what is multiplier, what is multiplicand, what is multiplier. Okay. So in this example, we consider 1010. That was multicand. I just put mcand, and this one multiplier, multiply. Okay, so this is okay. What's happening in this algorithm, in this flowchart? We are checking multiplier 0, least significant bit. If it's 0, we don't do anything. We just shift. Okay. If it's 1, we add multiplicand with whatever was inside this product as a result, and put that in this, and then shift. Okay. So to understand that, I'm gonna have this example in this diagram. Okay. So here is important. Just listen what I am, try to explain this. First of all, see which part is combinational, which part is sequential. You tell me, multiplicand, is that a register? Yes. Multiplicand, here is a register. So this is sequential. ILU is just, this ILU is just adder. So adder, is it sequential or combinational? Combinational, doesn't have clock, combinational. What is this? This product is also a register. So register also is sequential because it's memory, Control. Is control sequential or combinational? Control is like a decoder. It's combinational. We have another register, this shift multiplier. This is another one that this is sequential too. Okay, so as you can see, we have 3-part sequential and 2-part combinational. And we have 1 clock. I didn't draw here, but I'm gonna draw it right now. This is the clock. Okay, which part I need, which modules I need to connect this clock to? Just to sequential, correct? So I'm gonna connect this to this, and they are all synchronized together with the same clock. This is very important. We don't have 2 clock for computer. Maybe, but the normal computers have one clock. Maybe you design a computer too. If you see any advantage of that, we don't know. If you think, yeah, maybe we have a computer with 2 clocks. Some part of computer need to like slower, some faster. We're gonna design a computer soon, and we can see you can be creative in that case. Anyway, so this clock going to this because it's a register for putting the result 128. Why 128? Why? Double, yes, because the product it can be 2n, remember? But multiplicand is also 128 in this design. This design is not very good optimized. You can see another optimized version. And this multiplier is 64. And this adder is also 128-bit adder, is a big adder. Imagine this adder be like a Reaper carry. So it's you need to, that's going to be very, very slow. Okay, so that's good. So we know where clock connecting. So now let's see how this algorithm can work. For this example, as you remember, multiplication was like that. We multiply 0 to the multiplicand, because 0 multiply with anything gonna be 0. We just write 0. And then shift this part, because I don't want to remove it. I shift the others all the way. So 1 multiply to multiplicand is going to be multiplicand by itself, because 1 is not changing anything. So it's going to be 0, 1, 0, 1. Again, shift. Again, 1 multiplied by multiplicand is going to be multiplicand 1, 0, 1. And 0 going to be all 0. The result going to be 0. Why I write that? Because I want to do it in this algorithm. I want to check it out. Okay, good. So now let's go to this algorithm. First of all, product is 0 at the beginning. I remove these extra things. I'm going to keep the clock, because clock is important. Okay, right now, this here is 0. I just put 4, but it's supposed to be 2 times, like 8 of zeros, but I don't want to make it mess. Multiplicand is 1, 0, 1, 0, and multiplier is 0, 1, 1, 0. Okay, we are in a first when we started. I change the color. Okay, what's happening? So the controller is doesn't need clock. Just check what is least significant bit. Least significant bit is 0. So it generates control output. Because it's 0, need shift, make here 1, make this one 1, 2. But because it's 0, in this algorithm, we don't need adding. So add is 0, product is 0, 2. So that means controller make, in this time that it has, probably is before coming clock, in this time, control unit, here is just control test, but normally it's a control unit, actually is a combinational logic, so doesn't need clock. So generate based off the value of least significant bit. Say, okay, this is 0. We don't need add. We don't need this part. So we just need shift. So shifter get 1, shift left, shift right, multiplier, and the rest 0. Okay, so what's happening? We are waiting to clock. Right now, we did our job. waiting for clock. Clock coming. When the clock coming, action start doing. So this becomes this, okay? Shift right, okay? This go shift left, 1 0 coming here, okay? So again, control check the least significant bit. This time is 1. If it's 1, we need to do add. So this become 1. My God. Yeah, this become 1. And right become 1 too. So what happening? When this become 1, ILU is 1. ILU is not sequential. So it's going to start working by itself. So we have this value and this value ready too. So it do addition and put it ready in the bus. So it's going to be 0, 0, 1, 0, 1. But we are waiting for clock. So when clock coming, what happening? This value gonna set because it's right. When the clock coming, this gonna go inside. And the shift gonna happen to 0, 0, 1, 0, 1. One shift gonna happen. So it's gonna be, this gonna be here. And we're gonna have another 0 here. Okay, so again, another least significant bit is 1. So control again makes same control signals. So it means add addition again happening. So this gonna add with new value. It's not 0 anymore. This is 0, 0, 1, 0, 1. It's gonna get add together and get ready, but it's not set inside the product. You just get ready in a bus because ILU is not a sequential circuit. 0, 0, 1. Okay, 1, 1, 1. Am I right? I think it's this. Okay, anyway. And keep going. I'm not going to go all of it. And it's going to do all these things and make results. And the control also going to count the numbers. It also has a counter. It can count the number. But this design is not an optimal design. Before finishing, I'm just going to see this optimal design as well. What about we just had 2 registers and one of them shift left, one of them shift right. What about we just have 1 register and use it for 2 cases? This design is called optimized multiplier design. It looks a little complex, but it's going to be a very optimized because it's not faster. Still, you need n cycle. If you have n bit, I forgot to mention in that this one. If you have 4 bit, you need 4 cycle because for each cycle you make one of these sub addition parts and then add them together, or sub multiplication part and add them together. So you need 4 cycle. Each cycle one of these addition and add them together. But again, in this design, also we need yes. Sorry, this is about the language. Did you share the attendance code for the quiz? Yes. Oh, sorry. Can I get that? Yes, 1982. Okay, so let's see what's happening here. So instead of having 128 multiplicand, this time the register is 64. Doesn't need that much because we are not shifting there. We are not shifting there. ILU doesn't need to be 128 adder. Just can make it 64. Just have 1 register here, but half of that related to a product, half of that related to multiplier. and shift that together. So this is very interesting. I'm just going to do example if we get chance. If not, we can do it next class. But um, why this is 129? This is so the 129 is for this extra carry. We might have extra carry here. This is not overflow. This is just carry that happening because of, you know, each step addition. Okay, I think there is no time, but this is very important. I wanted to let you know how we can think differently to make a design much optimized. This is too much optimized than the other. As you can see, this adder is half of the other one. Multiplexer, sorry, this register is half too. And you don't need that part, that extra part. You just need 120, 9, in this case, 9 because of one carry. We're going to talk about that next class. Okay, what else? Okay, any question? Yes. Quiz Friday. Yes, we have. Yes. Yes, always we have quiz Fridays. Yeah. Okay, have a good day.